already on board afterwards. I had it published last year, and it's something I've been working on since about 2004. My motivation was to try to understand relativity and general relativity in terms of the fundamental state of space and time. And there were some issues that I had. And I looked at time dilation and length contraction to start with. And these two things have kind of an inverse relationship. And that sort of implies that time itself is not an independent variable. And one of the conclusions I started with as an assumption was that all particles move at the speed of light, at c. I was also troubled by the idea that rapidity was given by a hyperbolic tangent, and we have this sort of relationship with length contraction and time dilation, because that implies a more circular cos and sine relationship. So I was looking at just our real basic special relativity. I'm sure we're all familiar with this. We have a massive particle. We have energetic particle. And it might be obvious, and I certainly knew this ahead of time, but this is actually drawn as if there's another massive particle sitting here at the origin. And obviously anything like a photon that behaves the same way under every application of the theory is not itself described by the theory. So photons, of course, are outside the theory of special relativity. But this mass at the origin was troubling. And part of the reason that it's troubling is because we think of an axis as being stationary. So if we have a zero vector here, that means that we've lost some information because we don't know what direction that vector is pointing in. So we need a frame of reference that's not completely stationary like that. Now, we look at different models of the universe, and contraction and expansion are the two common ones that we talk about. There's problems with those. For example, they're not isotropic. So they're not really valid for a source of motion. And of course, we still need to explain things like the redshift that we get from astrophysics and from experiments. So the idea that I had was, instead of using contracting or expanding space, if you look at an interval, we have our normal ruler here. Now, as proper time goes on, what's happening is that this space is actually decaying. And as time goes on, we get this. So how does this explain time dilation at different velocities? Well, if we have two objects here, and we have V1 and V2, let's say V1 is greater than V2 in our frame of reference. Well, as this is densifying or decaying, because V1 is moving faster, it's actually traveling through less points. And so that's the time dilation that it's experiencing. And V2 is, of course, slower, so the densification happens more over that period of time, and therefore it experiences more time, less dilation. One of the interesting things about this is that it is isotropic. There is no center from which it expands or contracts. And again, because there's no expansion or contraction, there's no need for dark energy. And in the end, what it's actually going to do is it's going to divorce gravity from space, and it's going to put all the forces on equal footing, which we'll talk about a little bit later. It also speaks to the arrow of time, because this moves in one direction only, and of course entropy.
Just put my computer up. Okay.
Now, there's one point I want to make, in that this densification looks almost exactly like contracting space. But that's only if you consider a test point. If you consider a test point, it's exactly the same as contracting space. However, it's important that you consider an object that has dimension, and that is what's going to make this different from contracting space. It's going to give you a different answer in the end. So mathematically, what we're going to do is we're going to define 3 spaces in total. So we have object space, and that's what we're familiar with. That's x and t. And we're going to be using a 3-dimensional space with a time coordinate, but for the purposes of this paper, it's sufficient just to do really one spatial coordinate. What we're going to find is that densification occurs along any path of constant velocity, and we can parameterize it to 1 dimension. So that's really straightforward. Object space is what we're familiar with. We have time dilation and length contraction as these 2 factors. It behaves pretty much the same as you would with like Lorentzian transformations and things like that. And now I'm going to also define proper space. And proper space is the important one. It's what I consider to be the true state of the universe. And it is the space that is densifying. Now, obviously, we don't see the densification directly, but we experience it in the form of these strange effects from special relativity. So this is going to be z, and we're also going to use proper time. That's a z. So we're going to look at intervals in both of these spaces, and we're going to have dz is going to be equal to some scale change times dx, where we measure dx, and this is what we're going to find. Now, our scale factor f is going to be given by the density of points here as it increases with time and proper time. So f is going to be given by dx plus c dt over dx. And you can see, it's a very simple substitution. You're going to wind up with dx plus c dt. Now it seems trivial to do that, but in fact it's actually not. And what we find is that this densification causes an apparent expansion. This is in the form of a boost now. So this appears to be an apparent expansion. And it's only an illusion of expansion because densification is the real cause of that apparent motion. But that's what we get. And then we can define a velocity, or really more like a speed, w, not omega, equals dz over d tau. And that's going to be given by, this is a temporal dilation coefficient, v plus c. Now, it's a plus sign here, and this is similar to the Lorentz transformation. The plus sign comes from the fact that it's more similar to contraction and expansion. And if you were to reverse this, you would just see that you get a minus sign. That's not important. And if you have any questions, please just jump in and stop me. And I know I'm talking fast, but feel free to do that. The reason, that we use this ratio is because we can't actually count the points, because the number of points in any interval is always infinite. So we use this ratio of infinities, which I thought is a little clever, to create the scale factor. Now, one thing I need to mention is that when we're measuring velocities, we always need to make sure that we use something called a proper frame. And velocity turns out to be more important than position. And we can kind of guess that that would be the case because we don't have any restrictions on position in the universe. The universe is apparently infinite. We can be anywhere we want and we can go anywhere we want. But we have this restriction that light speed is a barrier for us. So that kind of implies logically that velocity is more important and more fundamental than position is. So the special class of frames of reference that we have are going to be where the time dilation is the least. So there is going to be a special velocity in the universe where time is moving forward at the maximum rate. And any deviation from that velocity is going to cause a dilation in time because you're going to be off of that special velocity. So we're going to call those proper frames. And there are many of them because they can be anywhere just as long as you're at the proper velocity. I'm also going to define, just real briefly, what I call a stationary space, but I want to warn that this does not represent anything physical. It's purely a mathematical construct for the purposes of calculation, and we're going to be using y, and again tau. And we can repeat this exact technique to get that dz equals dy plus c d tau, and then we can define dy d tau as u, and of course we have v that we're familiar with over here, and we can easily manipulate these and equate them very simply. Now the reason that I created this space was because in object space we have length contraction, time dilation that move in opposite directions. I'm sorry, they're inverse. In proper space, these two things are the same. They're exactly the same. And in stationary space, they're completely absent. That's why we can do calculations here from these other two spaces. Now, what we're going to do is we're going to choose what sort of function that W is going to have. And we can pick lots of different equations. We cannot pick the circular transcendental equations because there's no representation of the imaginary I at all. And we're not going to actually need it for the kinematics itself, which is pretty interesting, I think. So we're going to choose this is equal to hyperbolic secant of phi times the speed of light c. And of course, we know that that looks like kind of a hump like this. And part of the reason that this is a new idea, I think, is because if you look at hyperbolic tangent, there is no function that goes from hyperbolic tangent to hyperbolic secant. There's a bifurcation here. And I think that's part of the reason also that I is incorrectly used as part of space and time in normal kinematics. So in order to progress through this, what we're going to do to look at relative velocities is we're going to take a relative velocity u prime, and we're going to take that as equal to u2 minus u1. And that just comes from this u here in stationary space.
5 minutes.
Thank you. W prime is going to be equal to u prime plus c. And this is a little bit odd to see this plus c here. But the reason that this plus c happens is because if we have, again, this interval, let's say we have a particle here and a particle here, even though these two are kind of at rest with each other, as time goes on and this interval densifies, this distance is also growing. So that's the source of this extra factor of c here. And then, of course, we have alpha prime is equal to w prime over, I got that backwards. This is v prime, alpha prime plus c. And alpha prime is going to be given by e to the minus phi2 minus phi1. And this is the temporal coefficient for the relative velocity. Now, the reason that this is a minus sign is because it's possible between two objects for you to be in either the time dilated state that's more time dilated or less time dilated. So this can actually exceed 1, which is not normally possible in the current theory. So, given all these things, you can put all this together and you will end up with a rapidity c times tangent h phi2 minus phi1. Now, this is slightly different than Einstein's composition of velocities, and the reason for that is because his choice of frames of reference in his composition is a little bit imperfect. So in his example, it's a plus sign, and you have this ratio of tangents and other functions, but it's really more appropriate that it's a minus sign, and that's more correct. So I'm sure I'm running out of time. This does also have an effect on quantum mechanics. So I think it's interesting. I think it's a good start. I was interested in Peter's talk about quaternions because we have a space that's three-dimensional and real, and what we're going to end up with, I don't have enough time really to finish it, but what you're going to find is that the imaginary and complex quality is entirely associated with mass. And mass and energy are going to be 90 degrees out of phase with each other, and that's also what causes this confusion about quantum mechanics and why everything seems to be moving at the speed of light c, even though, yeah, so that's why. So, I'm sorry, do we have any questions? Really
I'll donate 10 minutes if you want to use it.
I'd be happy to. I don't want to step on your toes.
No, that's all right. I don't need 40 minutes. I can do 30.
Okay, so, it's my opinion that E equals mc squared is overdetermined, and that all particles move at c, and because they're 90 degrees out of phase between mass and energy, it appears as though energy moves at the speed of light to all mass, and mass moves at the speed of light to all energy. Yes, Peter.
I mean, zeta Bewegum, all particles move at the speed of light. It's just that they're in and out of vacuum. In the explanation of that, all particles actually move at the speed of light, irrespective of the mass. But it's not in a straight line, it's zigzagging into and out of the vacuum.
Into and out of the vacuum.
Is that of interest to you in this context?
I'll certainly think about it, but it's not my interpretation.
So what's the formal title of the presentation?
Proper space kinetics. I'll have to write it for you, along with my name. And the paper is available online, of course. There's certainly quite a bit more than I would like to say, but I mean, limitations of time, of course. But you know, it's something I worked on for quite a long time, and the idea was fairly straightforward to me. But the math took me approximately 8 years to work out. Not that that's my best subject necessarily. There's a lot to it. I can certainly talk quite a bit longer about that. More questions, I'm sorry.
Do I understand correctly, the fundamental input is the idea that space is decaying?
Yes.
And everything, this is what follows from. How do you imagine that? Is that an optical illusion or an artifact of expression or a physical process or?
It's a physical process, I would say. Now, interestingly about it is that because we have this spatial decay, we don't actually need a time coordinate. It's really convenient for the equations, but we don't actually need it. I tend to think of it as the ordinal numbers. If you wanted to look at the size of the universe, you could look at either the diameter or the width or something as being an omega. And as time goes on, not really time, but as the universe progresses, this omega squared, omega cubed, dot, 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 increases. And of course, that's an infinite progression. We have an infinite amount of room to change. And the reason that you use a power is because you have to keep these points in the exact same position that they were. They're not allowed to move once they're there. But of course, we're creating new points all the time as the universe gets broken down. So I think a decay process is is pretty attractive to physicists in general. I'm not sure that answers your question, but that's how I think about it. Yes, James?
Could you possibly think about it such that as time goes past, the present moment is here, but as we go past the present moments, then space is decaying into the past?
Decaying into the past?
Yeah. Does the past exist now, somewhere that maybe, is the past a place that maybe someday with better science we can go to, or has it decayed away? That is a question that some scientists ask. Does the
Sure.
future really exist, so can we go to the future?
In my opinion, from densification, no. Once densification happens, how would you reverse that?
I don't know, I just can't see how you can say space is decaying, because decaying is a process that takes time. And there's a present now, and that's what we're experiencing, the present now. So how can time be decaying during a present now, the moment?
How can time be decaying?
Well, how can space be decaying? The decaying takes time, it's a time process. How can that happen in the present now, which is what we're observing?
Maybe nilpotency has a rate.
Well, the reason I like this omega is because you can think of it as like increments. And each time this omega gets ratcheted up one, that's similar to a tick of the clock. And that's going to be your minimum time value, your minimum time interval you can have. But you don't really need it. I'm not really sure I'm answering your question about present and past and future.
Watch a sci-fi movie called The Langoliers.
Langoliers, Stephen King?
Yeah, something like that, if you watch the movie. He has a past decaying over a period of time, and people get stuck in that past moment that's decaying into time. The Langoliers are the guys that gobble up time and rebuild the future.
Right, with the airplane, now I remember.
Yeah, well, that's what I'm asking, sort of like that. How are you defining the present moment now? Is space actually somehow decaying within the present moment now that we are experiencing?
Yes, because we wouldn't experience time if it wasn't decaying like that.
Okay, that was my question.
Is there any observational data for the decay of the space or the universe?
No, I wouldn't imagine so.
How would you look for observational data on this?
I thought of a couple things. One thing is this idea of proper frames. This means there should be a frame out there, a frame of reference, a whole class of references, where time dilation is at its minimum. And every observation that we make should be, this is going to give you synchronicity between all the possible objects that are out there in motion. So that's one thing that we can look for. And actually, it doesn't really require a new experiment, just data out there that we could use. That's not really very definitive, though. One of the things I didn't get into about this idea of mass and energy being out of phase is that even though we have a massive particle and an energetic particle, they're going to have individual velocities of their own. Now, we know that this photon is going to be traveling, of course, in one dimension, either left or right. And what that's going to actually end up being is that's going to be the relative velocity in proper space between these two things. That's going to determine whether or not it's traveling left or right, whether or not they're separating or attracting. And of course, this is always going to be seen to be traveling at the speed of light. And it's one of those things where we can't actually observe it, of course. We have to make a measurement of it. But if we were able to have some kind of source here that would generate exactly the same photon time and time again, and that's going to be difficult, but if we could do that, and then we could modify this velocity of this object, what should happen, according to my theory, is that even though this thing seems to be traveling at the speed of light, there should be a finite velocity that we can give this, where this thing is going to turn around and suddenly look like it's heading in the opposite direction. But of course, the only way to do that is to be able to generate multiples of this that are exactly the same, indistinguishable particles.
3 minutes.
Thank you. Yes, Albert.
You said the proper frame is a frame where the dilation is at a minimum.
Yes.
But recording relativity, every observer who is in some inertial frame will say my system is a system where dilation is at a minimum.
Yes, but you talked about, in your talk about the twin paradox.
Yeah.
Well, this answers very clearly which twin is going to age more. Because if you relate both of their motions to a proper frame, you're going to find out which one is dilated more, which is dilated less.
In the case of the twin paradox, one of them is changing his frame, the frame in which he is really living. The one who returns changes the frame. So this principle is violated in that moment, if you say it that way. But if every frame is moving constantly, no return, no acceleration, nothing like that, then this cannot be decided. I believe that there is some proper frame, but the problem of special relativity is, in practice, there's no way to find it, to find which one it is.
Well, of course, we know that certain particles decay. We have clocks that work on that principle. And we know that in certain frames of reference, that decay takes longer than we expect because it's in an accelerated frame. Like particles come from the sun. Was it neutrinos that were hitting the Earth?
Yeah, but everyone uses his own clocks to measure the decay time of a particle, and everyone comes to the conclusion that in his frame of reference, the lifetime of the particle is the longest one. That's always the same way. I think there is a fixed, that's my personal opinion, a fixed reference, system of reference, which is at absolute rest. But the problem is we do not have any means in physics to find that one.
Bring it nearer.
Yeah, my opinion is that any frame of rest is a forbidden frame of reference. So rest is really taboo.
That's all right.
That's one way to see it, yeah? And the other one is there is one, but we cannot find it. There is one absolute one at rest, but we cannot find it because our physical means do not give us the tools to find
Well, I
it.
think we'll be able to find this. I'm sorry, I don't want to cut into any more time.
Okay, thank you.
Thank you very much for your attention.